Okay, so in this example we have the disk which is rotating at a non-constant rate of omega about a fixed axis passing through its center O. At this particular instant we're told the acceleration vector of point P on the disk is given to be the acceleration of point P. Based on this information we're asked to find the angular velocity of the disk at this instant as well as the angular acceleration of the disk. Okay, to help us out here what we're going to do is start by defining some unit vectors, and since we have some nice Cartesian coordinates already laid out here, I'm going to choose to use the I and j unit vectors. My next step is to relate the 2 points where I know the most information. In this case I know the acceleration of point P exactly, and I know the acceleration of point O exactly because it's a pin joint. So in this case I can say that the acceleration of point P is equal to the acceleration of point O plus the unknown angular acceleration of the disk, which I'll call alpha, and I'll cross that with the position vector P with respect to O, and then because this is a planar problem I can subtract from that R of P with respect to O times omega squared. At this juncture I can go ahead and make some substitutions to get the answers that I'm looking for, namely the angular velocity omega and the angular acceleration alpha of the disk. Here's how we'll do that. We'll start by saying that the acceleration of point P can be written as some value apx, a known numerical value in the I, plus apy, another known numerical value in the j. That's going to equal the acceleration of point O, which is 0, plus alpha, which can be written as an unknown scalar alpha in the k direction, cross r of p with respect to O, which in this case is going to be minus r in the I direction. I can then subtract from that the unknown value omega, quantity squared, times r of p with respect to O, which is again minus r in the I direction. If I expand what's happening on the right hand side here, I'll have first of all k cross I, which gives me j, so I'll have minus alpha r in the j, and then I'll have plus omega squared r in the I. Now at this juncture it's prudent to remind yourself that a vector equation in two-dimensional space is actually two scalar equations, so I can break this up into its I and j components. If I look at just the I component, I'll have that apx is equal to omega squared times r, and if I look at the j component, I'll have that apy is equal to minus alpha r. Let's go ahead and call these equations 1 and 2. If I go ahead and solve for equation 1, what I'll get here is that omega will be plus or minus the square root of apx divided by r. And if I want to write this in vector form, which should always be the case, we can append a k to this. Interestingly enough, if you're only given the acceleration of the point, you actually can't determine whether the disk is spinning clockwise or counterclockwise, hence the presence of the plus minus symbol here. If I solve equation 2, I'll get that alpha, the angular acceleration of the disk, is equal to minus apy divided by r. And in this case, if I want to make that into a vector, I can again simply append the k direction. Alright, I think from here we've already identified the angular velocity and acceleration in the disk, the two quantities we've been asked to find. At this juncture all you need to do is plug in some numerical values and you'll be good to go. Best of luck everyone.